Good day, my name is Katerina, and I would like to present our lab of wave processes and control systems with the project benchmarking the full order model optimization-based imitation in the humanoid robot reinforcement learning work. There are two main approaches to designing a walking controller. The first one is based on classical techniques, mostly mathematical optimization, and the other one involves machine learning techniques. Both can be used together and complement each other. The DeepRL approach is capable of independently exploring the dynamic capabilities of the robot model and generating robust locomotion. However, this approach has a strong tendency to fall into suboptimal local minima, resulting in visually unattractive gaits, especially for robots with a high number of degrees of freedom. Some forms of the reference trajectory can be added to the learning process to mitigate unnatural behavior. This methodology is being widely considered for the Casey series of robots from Agility Robotics, where in our work we studied the gaits of a humanoid robot with additional degrees of freedom, and the resulting motion can be directly compared to human walking. The simple reference trajectories in the form of heuristic analysis can improve the overall system performance. The more advanced approach is to use some model-based optimization techniques to generate a reference motion. These techniques can use a reduced order model or a full order model. In this work, we use the FORCed framework based on the hybrid zero dynamics approach to generate a gate library. This library can be used to directly control the robot with feedback controllers. Using only the gate library is marginally stable and requires an additional heuristic-based controller. This paper deals with the implementation and qualitative and numerical analysis of the full order model optimization-based imitation in the training of the humanoid robot model. Our first contribution is to evaluate the effect of imitation reward on the learning process of bipedal locomotion. Our second contribution is benchmarking the resulting robot gaits. And our third contribution is the implementation of these gaits on the new full-size anthropomorphic robot model with torso and arms, and finally, successful sim-to-sim control policy transfer. Our humanoid robot model contains 6 degrees of freedom for the legs and 3 degrees of freedom for the fully actuated pelvis. Using the humanoid model with a fully actuated pelvis requires a high-quality control policy because the motion of such a model can be directly compared to human walking. We prepared 3 gates. In gate 1, we used only the imitation reward. In the gate 2, we chose a near optimal ratio between the imitation reward, the taking command rewards, and the rewards penalizing inharmonious behavior. And in the gate 3, we did not use the imitation reward at all. The FORCed framework was used to obtain the reference trajectories.
Here is the implementation of anthropomorphic walking using deep reinforcement learning augmented with a whole body motion optimization. We simulated a humanoid robot model with a height of 1.62 meters and a mass of 65 kilograms containing 23 degrees of freedom. This robot model was designed by our lab to represent a generic humanoid robot with torque control. The anthropomorphic robot was trained to move along a plane with a given commanded linear and angular velocities. The main task was to achieve a visually attractive symmetrical gait similar to human movements while being resistant to pushes. To derive reference trajectories for the comprehensive robot model, the FORCed framework was employed. Within this framework, following the hybrid zero dynamics approach, we curated a gate library containing joint trajectories wherein the robot model traverses a horizontal plane in all directions with a maximum lateral velocity of 0.4 meters per second and a longitudinal velocity of 1 meter per second with increments defined at 0.1 meters per second intervals. We provided a sim-to-sim transfer to the PyBullet simulator where all the experiments were performed. By transferring to another simulation setup, we wanted to check the stability of the control policy since we couldn't perform sim-to-real transfer due to unavailability of a real robot. To achieve a more human-like gait, imitation learning were used. We calculate the difference between the actual position of the joints or feet and the reference ones provided by FORCed framework. All this is only used to train the control policies. To compare, we set 3 modes of training. The first one included only imitation rewards. The second included the combination of imitation rewards and others like following linear and angular velocities, keeping the joint in their limits, or termination penalty. The third train used no imitation rewards at all. As an input, the neural network takes the clock input describing the phase of the gait, the linear and angular velocities of the robot base, body orientation, target velocity commands, current positions and velocity of the robot's joints, and previous sections. The policy was aimed to generate the target positions of 23 robot motors at 50 Hz, and then the PT controllers actuated the joint torques at 1000 Hz. To perform the trains, we used PPO reinforcement learning algorithm. The first agent was able to work with a full body involvement, but in an unstable manner, while the locomotion of the third was more stable, but also more fractional and jerky. The second policy was the most resistant to the application of external pushes and produced a natural gate. It was achieved by balancing imitation, following the commanded velocity and penalizing rewards. We iteratively adjusted the weights of the positive rewards so that their average values were approximately the same for each episode in the training setup. We tested and compared these three control policies in terms of command velocity accuracy, robustness, energy efficiency, and visual appeal. The first experiment shows the difference in following commanded velocity. The task for the robot was to reach a target velocity of 1 meter per second when moving forward from a linear velocity of 0. A control policy that only used the imitation rewards during training, so the gate 1, was not able to accelerate the robot model enough to reach the maximum speed. In gate 2, the amplitude of the periodic deviations from the target velocity is greater than in gate 3 because the robot's movements are freer and softer due to the imitation reward. So in terms of following command velocity, both second and third policies performed well, but the last one was a bit better.
We test the robustness of the three resulting control policies in the pi-bullet environment. The recovery is triggered by all control policies are presented on the slide. One can notice a significant increase in robustness as the proportion of imitated rewards in training decreases. To investigate this effect, we carry out three experiments with linear, angular, and combination of both impulses applied to the robot. False or successful recoveries from pushes were recorded. Here one can see the response to applying a linear impulse to the torso. Clearly, the third approach can handle far more cases than other approaches in terms of sustainability. Policies that include reference trajectories showed roughly the same robustness. But the second experiment have demonstrated that the second gate of a suboptimal balance of rewards outperforms the pure imitation learning policy by 12% in terms of robustness against angular impacts. In the third experiment, we perform a linear and angular impulse to simulate the force applied to different parts of the robot. While the first gate has a lower push recoverability, the others are capable of rejecting significant impulses. To summarize the overall robustness, we can conclude that it increases as a proportion of imitated rewards decreases. An important aspect of any gate is energy efficiency. One of the relevant criteria for measuring the energy efficiency is the cost of transportation. It is defined as the ratio of energy consumption to weight times distance traveled. To separate the efficiency of the controller and mechanical design from the efficiency of the actuators, two specific metrics can be calculated. In our experiment, the cost of transport was calculated as the average value of 220 samples when the robot moves forward at a speed of 0.5 meters per second in flat surface. The cost of transport of the three gates is shown in the table. The results indicate that the first and the second gate have a lower value of the metric and are closer to the human one. To summarize, the higher level of energy efficiency demonstrated by gates that include reference trajectories. We conducted a user study to determine how natural the generated gates were. For this reason, we provide 3 videos of the obtained gates and ask users to rate the naturalness and coordination between the robot's legs and upper body. 51 users were involved in this procedure. Most of them have never worked with working robots. Some of them have experience in the field related to human anatomy. The user evaluation confirmed that training with reference trajectories resulted in a more anatomically correct gait. Although gait 2 is less natural than the gait 1 according to the user's pattern, the metric of coordination between legs and torso with arms was found to be equally high for both. To summarize, it can be concluded that according to the survey, gates with reference trajectories are more natural and anatomically correct. So, say control policies were developed and compared with different ratios of involvement of reference trajectories generated by the full-order model optimization method. The first gate was trained using only the imitation reward. According to the survey, it proved to be the most visually appealing. The second one found an optimal balance between imitation rewards and other rewards that encouraged walking and penalized non-anatomical behavior. It showed the best energy efficiency, as while keeping the benefits of near-optimal reference trajectories, the control policy improved the metric due to the torque reduction reward. The third gate didn't use imitation at all. It turned out to be much more stable than others. Overall, the second gate remains both natural and robust. In the future, we plan to implement a sim-to-real transfer of this policy. Thank you for attention.